Hello class, welcome to the Stat 511 Week 14 video on simple linear regression. In this video, we will begin by discussing the introduction to regression analysis. Then we will take a look at what is the best line to use in describing how y varies with x. Third, we will quantify the strength of any apparent linear relationship between x and y. Then we will take a look at any caveats about the practical use of simple linear regression before finally taking a look at the chi-squared goodness of fit test. Let's start with our introduction to regression. So for us, regression concerns quantifying the relationship between variables, meaning predicting some response y on the basis of one or more predictor or explanatory variables x1, x2, all the way to xm. In our ANOVA discussion, we had a continuous y variable and a nominal x variable. In regression, both x and y are continuous variables. Let us start by taking a look at an example. In statistics, there are a few famous data sets. In this course, we will use one of those famous data sets to motivate our understanding of regression analysis. This dataset is commonly referred to as the real estate example, and it concerns the dataset from a 1986 real estate appraisal article. So in this article, we had two variables of interest, selling price and size, where selling price is the selling price of a home per 100, I keep wanting to say 100,000, per $1,000, and size refers to home size, which is in measurements of 100 feet squared. We will have our predictor be size and our response be selling price. It should logically be the case that the larger a home size is, the larger a selling price is, or at least that's what we are expecting, but we can take a look to see if that's really the case. So in our case, the simplest possible version of our regression problem is in the case where there is a single x to predict or explain y, and that relationship between x and y is approximately a line. This situation is known as simple linear regression, which is abbreviated as SLR. Our textbook discusses SLR both descriptively and inferentially in Chapter 7. Chapter 8 is referred to as multiple linear regression, and it has multiple x's to predict or explain a single y. But that is beyond the scope of this course, simply because we've run out of time. And so for us, there are two basic descriptive questions that we are interested in. One, what is the best line to use in describing how y varies with x? And second, how may one quantify the strength of any apparent linear relationship between x and y? These two questions will be the basis of our next two objectives. Let's begin with our first question, and that is, what is the best line to use in describing how y varies with x? The traditional answer to how to choose a best fitting line to describe an XY dataset is to apply this principle of least squares. This involves looking for a line that makes as small as possible the squared vertical distances from plotted XY points to our line. Pictorially, this means that we will jiggle the line and try to find a situation where that sum of differences are as small as possible. Let's take a look at this pictorially because I feel like it's easier to understand. In our image, we can see an XY coordinate plane. We see this black line with the equation y equals beta naught plus beta 1x. You may recognize this as the y-intercept formula for equation of a line. We will be using this equation of a line formula throughout this lecture. This is what we will use as our line of best fit. You may notice these black dots connected to these red triangle or red squares. These black dots are each of our observed responses, y, to our predictor x's. We are interested in the distance between our observed xy data to our line y equals beta naught plus beta 1x. We want this distance to be as small as possible. Now, the issue with this idea of having things above and below the line gives us an issue of directionality, which is often represented with positives and negative, above the line being positive, below the line being negative. And for distance, we really don't want to have to deal with positive and negative. We are just interested in how far away our actual observed value is from our predicted line of best fit. So for that reason, we want all of our distance to be positive, so therefore we simply square it. So we want our sum of squared distances to be as small as possible. We want the distance between our actual values and our predicted line to be as small as possible, because if the distance is small, that means we predicted well. Or it means that there's a good relationship between our predictor variable x and our responses y. Algebraically, the problem of fitting a line is to choose a slope beta 1 and an intercept beta naught to make as small as possible the quantity, which is the sum of our quantity of y, which is our observed y's, minus the quantity of beta naught plus beta 1 x. These are our expected or predicted y's, or theoretical y's, I suppose, and quantity squared. This may seem familiar to you as when we discussed our sum of squares error, where it was actual minus predicted. That's the same case here. We are trying to limit the difference between what is actual and what is predicted. So this is a nice calculus problem that has a very simple solution. And so as it turns out, the best slope is beta 1 hat, which is equal to the summation of x minus the sample mean of x multiplied by the quantity of y minus the sample mean of y, all over the summation of the quantity of x minus the sample mean of x. And the best intercept is beta naught hat, which is equal to the sample mean of y minus beta 1 hat as calculated above, multiplied by the sample mean of x. These are what we call our least squares slope and intercept. In our real estate example, we could use those formulas to calculate a sample slope or a least square slope of 1.9 and a least squares intercept of 16.01. So this would make our least squares line or equation to be y equals 16.01 plus 1.90x, where y is the price in $1,000 and x is size in 100 feet squared. So what does that mean for us? So if we were to judge in that area and in the year 1986, the price of homes under consideration increased at a rate of about $19 per foot squared. If we were to use statistical software, this would be an example of one of the printouts where our line of best fit would be selling price equals 16.008135 plus 1.9000992 multiplied by size. Now let's try to go ahead and do this by hand. For the small fake data set below, let us try to find our best fitted line by hand. So we are given values of x to be -2, -1, 0, 1, 2, and values of y to be 4, 3, 3, 1, -1. To begin, we're going to need to calculate our sample means for x and y. Our sample mean for x will be 0, and our sample mean for y will be 4 plus 3 plus 3 is 10 divided by 5. So that'll give us a sample mean of 2. Now we can begin by subtracting each of our observed x's minus their sample means. And as we are subtracting by 0, it is a pretty quick difference to find. Now we can do the same for our y values. 4 minus 2, 3 minus 2, 1 minus 2, and -1 minus 2. Now using our previously two calculated columns, the next two columns would have us square each value to be 4, 1, 0, 1, 4, 4, 1, 1, 1, 9. And finally, our last column would have us multiply our first two calculated columns together to be -4, -1, 0, -1, and -6. This table is not necessary, but it is a nice, easy way to be able to calculate our desired values. So at this point, I'm going to add up my columns. And I'm going to do it for all of my calculated columns, although I really only need the last 3. For my first two calculated columns, I find they add to be 0. For my summation of x minus x bar quantity squared, I have 10. For the summation of y minus y bar quantity squared, I have 16. And for my last column, I have -12. Now, there are abbreviations for our last 3 columns. We know these as our sum of squares, or SSXX, SSYY, or sometimes known as TSS, and the last one, sum of squares, XY. The first two calculated columns do not have any abbreviations, but they are helpful to check. These two columns should add up to be approximately 0. If they do not, that is a good indicator that you have made an error somewhere in your initial calculations. Now that we've completed this chart, we can easily calculate our least squares slope and intercept. So just to review, we calculated our sample mean to be 0, for x, sample mean for y to be 2, our SSXX to be 10, our SSYY to be 16, and our SSXY to be -12. Using the equation for our least square slope, that is the summation of x minus x bar multiplied by y minus y bar and quantity over the summation of x minus x bar and quantity squared. This is equivalent to our SSXY over our SSXX, which is -12 divided by 10. So this will give us a least squares slope of -1.2. Now we can go ahead and calculate our least squares intercept, which we may recall is y bar minus beta 1 hat multiplied by x bar. And so this would be 2 minus negative 1.2 multiplied by 0. And so our beta naught hat, or our least squares intercept, will be 2. This will give us a line of best fit of 2 minus 1.2x. And so that brings us to the end of our first question. What is the best fitted line? We have now just pretty easily demonstrated it. So this brings us to our third objective, and that is to be able to quantify the strength of any apparent linear relationship between x and y. So an initial measure of association between two variables x and y, we will call this statistic the sample correlation, the sample linear correlation, or my personal preference, which is the correlation coefficient R. R is equivalent to the summation of x minus x bar multiplied by y minus y bar in quantity all over the square root of the summation of x minus x bar quantity squared multiplied by the summation of y minus y bar quantity squared, which you may recognize as being equivalent to SSXY over the square root of SSXX multiplied by SSYY. From our real estate example, we would find a correlation coefficient to be 0.9379. But what exactly does that mean? Well, here are some facts about our sample correlation statistic. 1, this statistic must be between the bounds of -1 to +1. If R is exactly +1, then all of our xy points fall on a single straight line with a positive slope. If R is -1, then all the points fall on a single straight line with a negative slope. And so one way we can indicate the slope of the line is by calculating our beta 1 hat formula, as their slopes, or their signs, I should say, will be the same. Now, it will be a rare case where you have your correlation coefficient to be exactly 1. So when we say that R is near plus or minus 1, we see that as indication of a strong linear relationship between an x and y. And when R is near 0, we see that as an indication of a lack of linear relationship. And so in our real estate example, we have R being equivalent to 0.94. So this would indicate a fairly strong positive linear relationship between size and price. In our small fake data set that we've been calculating by hand, we would calculate our correlation coefficient to be negative 0.9487. So this would indicate a fairly strong negative linear relationship. Now that we've discussed the correlation coefficient, there is actually a second measurement of linear association, and it is called the coefficient of determination, and it is abbreviated by R squared. And this is built on two measures of variability in the y's called the sum of squares. The first one we're interested in is the total sum of squares. You may be familiar with this statistic from when we discussed ANOVA. So our TSS is equivalent to the summation of y minus y bar quantity squared, or as we've used it in a few slides already, SSYY. And it is a measure of our total variability that exists in our response y. The second sum of squares that we're interested measures the variation not accounted for, leftover, residual, or error after fitting an equation to our data set. So it's the variation that was not accounted for by the equation we fitted. And to abbreviate this, we have mu hat of y given x1, which is the prediction of our response of case I from our fitted equation. And so we let our error term to be yi, our actual observations, minus mu hat of y given x, which is our predicted value of our response. And in other words, our error terms are a measurement of our residuals, or what's left over from the actual minus the predicted. And as we are referencing actual minus predicted, it should come as no shock that our sum of squares of these error or residuals is our SSE, or sum of squares error. It is equivalent to the summation of our error term squared, or the summation of yi minus mu hat of y given x quantity squared. And so for us, we then could calculate another measure of variation called SSR, but we'll talk about that in the next slide. Because in order to do that, we must first have an understanding of the relationship that exists between SSE and TSS. So in this case, since SSE is the measure of variability in the response not accounted for by the fitted equation, that would imply that it must be less than or equal to the measure of variation for the entirety of the response. So to understand this graphically, we let this red line be our linear fit. The red box is the distance that exists from each observation y to our predicted response. And as always, because we want these distances to be given in a positive number, we must square them. And our sum of squares total, or our total sum of squares, depending on the textbook you look at, sometimes TSS is given as SST. It calculates the average y, which in this case, for our small fake data set, you may recall that our average y was 2, and it takes the distance from each observed y to the average y and calculates that sum of squared distances. Now, as I established before, we know that SSE is less than or equal to TSS. So to make up the difference, we have TSS equal to SSR minus SSE. Excuse me a moment. And this SSR value is a measure of variation in y that is accounted for by the fitted equation. It is called the sum of squares regression. It is common to state as a fraction of TSS our coefficient of determination to be r squared equal to SSR over TSS. The formula is also equivalently written as r squared equal to 1 minus SSE over TSS. This is another difference that exists between textbooks and professors. Traditionally, I've seen more of 1 minus SSE over TSS, but I know our textbook uses SSR over TSS. And again, they are equivalent. And so how are we going to interpret this new statistic? Well, for r squared, it is a fraction of the overall raw variability in y, in some sense accounted for in fitting the equation. In this case, r squared will always be between 0 and 1, where the closer it is to 1, the stronger indicator of a linear relationship. The closer it is to 0, then we can determine that there is not a linear relationship. And so in our real estate example, r squared is equal to 0.8796. So this would mean that 88% of the raw variability in price can be accounted for or explained by using home size as a predictor or explanatory variable. So in the simple linear regression case, we can understand, as expected, that home size is a pretty good predictor of selling price. We can, of course, calculate r squared by hand, and we will do so using our small fake data set. To begin, we must calculate our predicted values, mu hat of y given x. To do so, we would find that our predicted of mu hat of y given x is 4.4, 3.2, 2.8, and negative 0.4. From there, we can calculate our error term by subtracting our actual minus predicted responses. And so we may find 4 minus 4.4 to be negative 0.4, 3 minus 3.2 to be negative 0.2, 3 minus 2 to be 1, 1 minus 0.8 to be 0.2, and negative 1 minus negative 0.4 to be negative 0.6. If you have done your calculations up to this point correctly, the summation of this column should be approximately 0. Now to calculate our squared error term, we must take the calculated column that we just did and square so that we will have 0.16, 0.04, 1, 0.04, and 0.36. By taking the summation of this column, we will have an SSE equal to 1.6. This means for our small fake data set, where we use the formula, since SSE is handy, we'll do the 1 minus SSE over TSS. We may recall that TSS equals 16 from our previous slides. So this will be 1 minus 1.6 over 16, which will give us an R squared of 0.9 or 90%. So we may say that 90% of our raw variability in y can be accounted for or explained by using our predictor variable x. And so, as it turns out, R squared can be thought of as a squared sample correlation. And so that is, it is always the case that our coefficient of determination is equal to the correlation, between y and mu hat of y given x quantity squared. And in this very special case of simple linear regression, the correlation between y and mu hat of y given x quantity squared is actually equivalent to the correlation between y and x quantity squared, meaning that capital R squared is actually equivalent to lowercase r squared. And so using our real estate example, we can verify this using our known values of lowercase r, meaning our correlation coefficient, and r squared, which is 0.8796. We may notice that in the simple linear regression problem, if we are given r squared, we are able to convert to our correlation coefficient by taking the square root of r squared and assigning it the sign that we calculated for the slope of our least squares line, meaning that beta 1 hat value. And so at this point, this does bring us to our caveats about the practical use of SLR. Once we discuss these 4 caveats, our simple linear regression discussion will be over. So here are the 4 caveats we have about using simple linear regression. 1, the least squares line r and r squared are very sensitive to a few extreme data points. Both r and r squared are measures of linear association only. 3, we must and should be aware of extrapolation. And 4, correlation does not mean causation. Let's examine these 4 caveats closely. So if we take a look at this scatter plot of ages and height in a class of Purdue undergrads, we can see that we have one student that is both older and taller than the rest of the class. if this single student is included with the rest of the data, our correlation coefficient is 0.33, which gives us a positive slope. However, if this person is removed from the data set, we can see that our correlation drops down to 0.03, which at that case, we would say that this does not indicate a linear association between age and height. So, what does that mean? Make sure you take a look at a scatter plot of your data and make sure your results aren't being unnecessarily skewed. Second caveat, you must remember that R and R squared work only for linear data sets. In this small fake data set, we have a rather perfect parabola. Using our x and y data set, we can see that this would be the equation of the line of y equals x squared. However, if you were to try to calculate the correlation coefficient, you would find that that value is pretty close to 0. Because while a very clear trend and relationship does exist, it is not a linear one. Our third caveat states that we must be careful of extrapolation. What is extrapolation, you may ask yourself? It's when we try to predict or explain our response beyond the bounds of the data we've already assessed or sampled. So if we take a look at this case, we see that we have a scatter plot of women from ages 40 to 80 and their corresponding muscle mass. We can see a pretty clear negative slope. So from this, we would assess that the younger a person is, the higher their muscle mass is. And while that is true from ages 40 to 80, you should think about the muscle mass of an infant or someone who's very young as compared to the muscle mass you have now. So to try to predict beyond the bounds of the current study, you may cause yourself to have an error. We can, however, do something called intrapolation, which is trying to predict results that are in the bounds of the sample we have already assessed and trying to predict with those. That is okay. So we may be interested in trying to figure out someone who's, say, 56 years old, and we may be able to say, oh, I think they're going to have about a muscle mass between 80 and 85. And that's okay. We can predict that rather or explain that rather safely. It's again when we go outside the bounds, when we have some concerns. Finally, our fourth caveat is that correlation does not necessarily mean causation. One example is that using sports, we may see that there is a positive correlation that exists between the number of fouls committed by a player and the number of points that are scored by that player. Now, one thing you wouldn't go do is have your coach tell everybody to foul more because if they foul more, they'll score more points. That doesn't make sense. That's not true. What happens is people who score more points often play more, and people who play more foul more. You can think of the same thing with skiing accidents and temperature. You would see if you mapped temperature in relation to skiing accidents, you would say that there seems to be a relationship that more skiing accidents happen when the weather is colder. Well, that has nothing to do with temperature. It's just that people ski in the winter. And so that brings us to the end of our discussion for simple linear regression. This brings us to our final objective of the course, and that is to talk about the chi-squared goodness of fit test. I do apologize for just kind of throwing this in at the end of the lecture. It is the last topic we need to talk about, and it is actually very short and very easy. And so it is a pretty short 5-minute couple of slides, but it is good for you to know. because it is used to determine if a population has a specified theoretical distribution. And so for each of our possible category of a categorical variable, an assumed probability of occurrence is specified, where our null hypothesis will be that some specified distribution is correct, and the alternative hypothesis is that some sort of specified distribution is not correct. So let us take an example. So imagine that a gambler wants to test to see if a particular die is fair. So the roll of a die has 6 possible outcomes: 1, 2, 3, 4, 5, and 6. If the die is fair, then we should expect each of these outcomes to be equally likely and to occur approximately the same number of times. The gambler decides to roll a dice 30 times and records the number of times each number comes up. So we can see in this table, we have each of our 6 possible outcomes and the number of times each number was observed. We call these counts the observed frequencies. And so for us, our null hypothesis would give us an indication that our probabilities need to be equivalent. And since there are 6 possible outcomes and each of them have an equally likely chance of occurring, we would say for our null hypothesis that the probability of P1, P2, P3, P4, P5, and P6 are all equivalent to each other and equivalently 1/6. Our alternative hypothesis would be that at least one of these PIs do not equal 1/6. And so in order to test this hypothesis, we need to determine what counts should be expected in each category if the null hypothesis are true. And these expected frequencies are the count that we expect if our null hypothesis is true. So in the concept of our rolling dice example, it is the expected number of times 1, 2, 3, 4, 5, or 6 should appear out of our 60 rolls. If the probabilities are specified in the null hypothesis, then we may calculate our expected frequencies to be E1 equal to N, our sample size or number of trials, times P1 equal to E2, which is equal to N times P2, and so on. So in our dice example, since the gambler rolled the dice 60 times and we had an expected probability of 1/6, 60 times 1/6 would give us an expected value of 10 for each of our outcomes. So if the null hypothesis is true, then the observed and expected frequencies should be fairly close. The larger the differences between our observed and expected frequencies, that is the stronger evidence against our null hypothesis. And so we now need to calculate a test statistic. So let K be our number of categories. We'll let O1, O2, all the way to OK be our observed frequencies, and let E1, E2, all the way to EK to be our expected frequencies. So therefore, our chi-squared test statistic is the summation of I equals 1 to K of each observed frequency minus its corresponding expected frequency, quantity squared, over its expected frequency. When our null hypothesis is true, the chi-squared test statistic has an approximately chi-squared distribution with k minus 1 degrees of freedom. And this is provided with the assumption that the expected frequencies are at least 5 or more. Think of this in the same sense of the binomial distribution, where we must have had at least 5 successes and 5 failures. And if you need a brief review, this slide was to remind you of our characteristics of our chi-squared distribution. We may recall that it is not symmetric. All values are greater than or equal to 1, and we will use the chi-squared table in order to find our critical value. So as a nice review for performing a hypothesis test, or in this case, a goodness of fit test, we begin by stating our hypothesis, calculating our test statistic, finding our critical value from the chi-square distribution tables, making a statistical decision to either reject or fail to reject our null hypothesis, and then finally writing a conclusion in the context of our problem. And so going back to our first example, we clearly were able to state our null and alternative hypothesis. So now we can begin the point of calculating our test statistic. And so using our formula, we will get a chi-squared statistic of 9.4. And we will compare this to a chi-square distribution with k minus 1 or 6, because we have 6 categories, minus 1 equals 5 degrees of freedom. We will assume an alpha level of 0.05, and so therefore using our chi-square table, we have a critical value of 11.070, and as we can see that 9.4 is less than 11.070, we will not reject the null hypothesis. And so this would imply that we do not have sufficient evidence to say that the probabilities of some of the possible outcomes are not 1/6. So that is, we do not have sufficient evidence to say that the die is an unfair one. We may also take a look at a second example where we are given a null hypothesis of P1 equal to 0.5, P2 equal to 0.3, P3 equal to 0.15, and P4 equal to 0.05. We were given 200 observations with 4 categories. We can see our observation for category 1 is 106, 64 for category 2, 24 for category 3, and 6 for category 4. Given that we know our sample size and number of categories, we can go ahead and also calculate our expected frequencies. Remember, to calculate an expected frequency, it is the sample size multiplied by its expected probability as defined by the null hypothesis. And so we can see that for categories 1, 2, 3, and 4, we can see expected frequency of 100, 60, 30, and 10. Taking a look at our observed and expected frequencies, it doesn't appear to be a huge difference between what was observed and what is expected. So just by taking a look at this, I'm not expecting the null hypothesis to be rejected, but maybe we'll get surprised. So to look at this formally, we've established our null hypothesis to be P1 equals 0.5, P2 equals 0.3, P3 equal to 0.15, and P4 equal to 0.05. And our alternative hypothesis is that at least one value of Pi differs from what is in the null hypothesis. Our test statistic would be chi-squared equal to 3.427, and we compare this to a chi-square distribution with 4 minus 1 equals 3 degrees of freedom, and a calculated critical value of 9.488. And since 3.427 is less than our critical value, we will not, as expected, reject the null hypothesis. So this implies that we do not have sufficient evidence to say at least one Pi differs from the value specified in the null hypothesis. And so this does bring us to the end of this lecture video. I tried to keep it short since it is the last week of class, and I do know that at least some portion of this lecture was a review. For this week, please make sure to read Chapter 7, Sections 1 through 4 and 7, and Chapter 12, Sections 1 through 3, and complete Homework 6. If you have any questions, as always, please send me an email. Have a good night.